Start recording. Okay, so your face is now live on the internet. Ladies and gentlemen, I'm Andrew Russell. This is Daniel Crenna, and Daniel, do you want to just give a bit of context to anyone who happens to watch this about sort of what you've asked me to do and sort of what you want to get out of it?
Yeah, sure. Okay, so I contacted Andrew. You probably know that we worked together on River City Ransom Underground. We spent 4 years programming together in the trenches. There was a lot of learning, mostly on my side, and we worked a long time on that game. And I've been a programmer for 28 years. I have a lot of experience in software development, but I was frequently, I guess, surprised, alarmed, excited, inspired by what I don't know about games. And I feel like, everybody has a coach, whether it's, Tiger Woods or, little old me wanting to, improve my game development skills. I think what a lot of people might realize or assume that when you're a developer, like a software developer, and you do business software or whatever, that you have the same skills that transfer over into game development, and it really couldn't be further from the truth. And so I think my experience at River City Ransom was like, I've always described it as going home at the end of the day and getting a math textbook and beating my head with it until that's how I went to sleep every night. So the idea here is, I think there's a glass ceiling. Like, I think I kind of represent a very typical situation of a developer that has, that understands like OO concepts and so on, but doesn't have the solid mathematical grounding that you need to make games. And I think that's the missing link. And so I'm not embarrassed or, too proud to get help. So I've asked Andrew to, after the game that we just made together, to help me get better at making games. And I think, so we're going to start from the very beginning of what I should know about making games, and I'm hoping to, do my homework and so on, and improve and produce smaller games, and I think this is going to help me in a couple ways. One is going to allow me to participate more regularly in game jams, because I think you have to have done several, maybe dozens, even maybe hundreds of small games to get that kind of under your fingers, so to speak, like the skill set you need, or the problems you're trying to solve. And I have never done a game jam before, so that would be nice. And also just to get just to get the basics, and go from there. And then my grand vision is to be able to, get back into things and make my own games, and not be afraid of the harder stuff that people tend to buy engines for.
Yep.
Hopefully that's a lot. That's a big talk, but
Makes sense. So, yeah. So in advance of this, I threw together what I figured. Like, we're planning to go for an hour, so I threw together sort of what would be like the first hour of stuff I would basically have someone do if they know how to program and have no idea about game development, sort of just to sort of figure out what is a good starting point. So yeah, I'm totally expecting a lot of this stuff to be like stuff we can just gloss over really quickly.
I hope that if we don't gloss over, it's not sending the wrong message, but we'll see. You're talking to somebody who's very afraid of math, who only understands it intuitively. And I'm already looking at this. I
Yeah.
mean, I get it, but you know what I mean? Like, I don't know why you've got the two pipes between the
Ah.
V and
Yeah. So I mean,
so
that's just notation, which helps to know. So I mean, let me
yeah,
open up screen sharing now, so
sure thing.
you can see what's going on. I'll bring up the paint program. Okay. So
This is GIMP, is it?
this is GIMP. Um,
Mhm.
just getting my window layout so everyone can see. So yes. All right. So basically, introductory 2D vector maths. So we'll start with like, so this should be like really obvious stuff. Is you have like a scalar, which is a number. Like in code, you'd be like float x is a scalar, and then you might have
Right.
vector 2v, and that would be like a vector. That's a 2.
Yep.
And that should be obvious enough. And like in there, you've got struct float
x, float y. Yeah.
y. So that's how you code that.
So we're just talking about terminology here, right? So it's like a single component number is a scalar, and a multi-component number is a vector.
That's one way to think about it, but there's a more rigorous mathematical way to think about it. And then if you talk to someone who's like an actual mathematician who does actual maths, they'd probably be like, they'd probably go a level above what I'm probably going to say, because all I know is just enough to do game programming and like know what to Google when I need more information.
Right.
So we'll get into what a scalar is sort of more technically in a bit. So the idea is you've got this multi-dimensional thing. So that could be like a vector 3, and you stick a z on the end, and then a w if you want a 4D vector and whatnot. And the way you sort of indicate that mathematically is like x, y, and I think we won't get into like matrices and stuff just yet, but that sort of notation starts to help when you do that. And like, so you could extend it out like that.
Right.
So that's a vector. So the first thing I wanted to like talk about was the difference between a scalar, a vector, a position, a line, and an array. Tablet issues. Okay, so when you have like a vector, that's basically, say this is our like 2D space. You've got the origin. A vector is basically an arrow pointing off somewhere to a location in that space. Whereas a position might just be, that's a point in the space. And sort of that's like an important distinction. Even though like this is represented like this is an X and a Y, and this is also like an X and a Y, they're sort of conceptually two different things. And you can interchange them, but it helps to think of them differently. Because what you can also have, because this position is represented by where you end up when you follow that vector there. You can also have like a line, which is actually made up of two positions, and it gives you, in fact, a line segment, whereas a line would be like the whole thing. And then you have array, which is like a position with a direction. Actually, array, now that I think about it, this is typically normalized. So that's sort of the idea, is that there is a whole lot of different concepts you can represent with, like, another way to explain this is a vector is a direction and a magnitude. So it's that direction going out that far, whereas the position is just a position.
Right.
So hopefully that all makes sense. I feel like I've just...
I mean, it does to me intuitively, because, I mean, maybe just because I've done it before, but yeah, I mean, yeah, it does to me. I don't know if I could like describe it on a test or something, but I've always intuited like the vector to be, something's moving somewhere, and it's kind of just a notation of what direction you're going and how what your like I think you said magnitude possibly.
Yes.
To me it's like I know it doesn't include velocity. I know it has nothing to do with velocity, but to me it always is like a movement indication. An array is like sometimes, like to me, I thought it might be like like when you say normalized, I'm thinking that you kind of chop off the magnitude and set it to 1, and then it's almost like 2 pieces of data. You have the position it started from, and then you have the vector that applies to it. Is that right?
Yeah, I feel like I'm having trouble like explaining this because like you're quite right, and that is like once you've worked with it a whole lot, you just sort of intuit these things, and you like look at the code. It's like, oh, that is a position, whereas that is like a direction and a magnitude, whereas that is like a vector that we transform. And
right, all it looks like is x and y to other people, but yeah, the position is like a static thing. I was here. Ray is like I was here, and also I'm headed over here now, and the vector is headed over here now part. And that's gonna sound stupid to anybody who does math, but yeah, I get it. And obviously, like a line segment is like a line goes on forever because there's no defined ending to it, and then a line segment is just like 2 positions, 2 static things that you connect them together, and you can produce, I guess, a magnitude between or a vector between those 2 points.
Yeah.
By just looking at where it started and where it ended. Yeah, I mean, I'm good, but like, yeah, I have the same sort of glossy, fuzzy.
Yeah. Well, okay. So that's good. So we get that. And then the idea behind like a scalar, like this is where we get like, you have a number line, and this is like a one-dimensional, like a position on this number line might be that, like that's 3. Whereas a scalar is also can be represented as like a single number, but a scalar is more like if I have a scalar of 2 and I multiply it by this one-dimensional vector 3, I get 6. I come out, out to here, and I get 6. So
why do you throw those lines on there again? Are you denoting that it's a scalar by doing that?
So these lines represent the fact that it is a vector. So the fact that this one doesn't have lines is like that's a scalar.
I see.
And so
I sort of see, because like I thought a vector had 2 parts to it. So why is there a 3 that's a vector?
Yeah. So what we've got is a one-dimensional vector. So this is like
I see.
This is like just the x.
This is why you can have. That's why when I said it was the scalar was single component, and vector was multi-component. That's why it was wrong, because you can have single component vectors. That's what you're showing me.
This is sort of the subtle part that I think is like important to realize. And like when you're programming, that's a float, and that's a float. But it's important that you sort of know what these quantities represent in the code, because this is a scalar, and this is a you can't see it because I don't have webcam, but quote unquote vector, and you're sort of scaling this vector by this scalar here, and the idea that's sort of the idea behind a scalar. And the idea is that works like if I suddenly like extend that out to 2D vectors, that still works.
All right, I'm totally now I understand the scalar part of it as actually you're saying it because you often like have to the easy thing is like when you zoom something, like want to show something on the screen at 2 times, you're going to scale it up to 2 times. That's why the float f or the float scale in your draw call is called a scalar, because you're scaling something. Okay.
Yep. So that makes sense. So that's like, so getting on to the next thing in this list. So that's like scaling vectors. So you multiply it by a scalar, and it gets bigger or smaller. And so it's just simple component-wise multiplication, and then obviously addition and subtraction. Like this should be like I don't know what happened here to my pad. Oh well. You have like x, y, x1, y1 plus x2, y2 equals x1 plus x2, y1 plus y2. So hopefully that is like really obvious.
I want to say the word commutative somewhat for some reason, but I don't know if that applies. There's rules about
okay, so this is where it gets into the actual math stuff, and this is exactly the kind of thing that I'm like, I'll just quickly Google that to make sure I'm right. But from memory, I believe that just means if you swap these two components, it doesn't matter, because if you swap those two, it gives the same result. Right. I think that's...
Yeah.
Oh, actually, no. There's commutative and then there's something else.
I'll go to con and I'll lambast myself later. But I mean, I get what this is, and I yeah, you're gonna add these two. You're adding these two-dimensional vectors together, and you just basically you can do that. You can add the x's and the y's together.
Yeah. So
yeah, it's not scary. This probably meant. Yeah, I don't have a good grounding on math terms.
So the important part there is like how that works geometrically. Like if you have a vector that looks like this, I don't know why my undo is not working. And let's up the production values here. If you have a vector here and then a vector like here. So these are two vectors. You add them, and what happens is it's basically, geometrically speaking, it's that, and you get, the result looks like that, and you end up out here. So it's like A plus B equals C. And being able to like visualize that is quite important. You remember all the stuff we did on River City about do you remember the things we did to get the automatic sprite sheet selection process and position those correctly?
Yeah, I mean, I remember doing it.
Yeah. There was a whole lot of diagrams that were sort of like this.
Yeah, I remember you did like one in the Mona Lisa gallery or something.
Yeah.
And you had the picture of you pointing to it. But yeah, I recall. I mean, yeah, I remember basically having, I didn't really understand it, but I think, yeah, the problem was we had a Bobo was bigger than the other sheets. We had to like translate those. We had to, like you just did there, you were adding vectors to get the right place to start cutting that sprite sheet so that a Bobo would be able to transfer the animations that Bannon drew into a larger body without blowing everything up.
Yeah, I think what it was, we had like a sample, and then we had to map it onto like some other sample that was at a different like position, and then we had to basically like figure out the external box.
Mm-hmm.
And then there was like a vector here, and we had to map that onto like there to figure out where in that box it corresponded.
That's right. Yeah, you used the same colors as you did during that exercise, so I'm starting to sweat a little bit. But yeah, I remember now.
So this is why like being able to visualize that sort of thing is important. The other thing I wanted to talk about was like subtracting vectors, which is really similar. So if we use the same vectors, it's like, for some reason my undo is broken. It's very odd.
Forward only.
Yeah. All right. So if we use the same vectors, the idea when you subtract them is basically you stick the arrowhead there and go backwards, and you end up here, and so the answer ends up being like that. And that one, obviously, unlike this case, you can't go swapping these two. But obviously the maths is the same as like x, y minus a, b equals x minus a, y minus b. So that's like the maths part of it's hopefully really obvious, and I mean you just use the built-in vector type if you're using like x and a or something. But being able to like visualize this thing is really quite important, because that's what lets you solve problems like this one, because like often it'll be like that is something we want to reverse, like we want to go backwards from there, like there.
Okay.
And obviously you can also negate a vector, so that's basically like taking away from 0, and it looks like this, which means that like the negated form of that red vector is just exactly the same vector going in the other direction. So that's, if that's vector a, then that is negative a.
Right.
So that should all be really simple.
It's simple. I haven't seen it presented that way before, like especially the subtraction bit, which makes, I mean, it makes sense. Like I can add and subtract vectors, but I never seen it look like the visual representation of it, where you're like, seeing where the arrow is going to end up. I mean, you do the math and that's what the arrow is, obviously, but showing it visually, that's interesting, and it does explain why I was so confused when we were working on the spreadsheet stuff, because like like you said, I wouldn't know where to begin, even though we just ended up adding and subtracting vectors. Although I think that was a lot more complicated. We had like magic matching and fuzzy stuff and trying to figure out what color pixel was there and all that. But essentially that's the same.
This problem here was like several steps of this.
Right.
And so basically, and what we had to do is basically draw out all of the operations sort of geometrically. So, and then go from that geometric thing to like the maths. And and what was really important on that one was keeping like the names of the vectors sort of accurate. So like on this one we'd be like, well, this is A, and this is B, and this is C, and then if we wanted like negative A, you'd make sure that is like labeled negative A. So you get this one here, and just keeping those labels all the way through and being like really rigorous about where those labels go. That's basically all you need to sort of solve these problems. It's just multiple steps.
Right.
So,
I get it. I mean, I think I get it.
Yeah. So that's not particularly complicated stuff, but just being able to do that and do that rigorously is important. So let's look at the next thing on the list, which is length. So this one is like Pythagorean Theorem, which hopefully is like really quite simple, and that is, if you have a triangle and you basically draw a square here and a square here and a square, what's the bet this goes off the canvas? Oh, it didn't. Square here. If these are all squared, if this is A, B, and these are lengths now, not vectors, C,
right.
The area of this is C squared, this is B squared, this is A squared, and what you find is that C squared equals A squared plus B squared. So does that all make sense?
Yep.
Okay. Now you know that if I take, like say, -3 and square it, it is equal to 3 squared. That makes sense to you?
It used to. I'm assuming that it. Yeah, because you keep flipping the signs every time you multiply, right?
Yes, exactly. So -3 times -3 is 9. Yep.
9.
Yep. Okay. So it doesn't matter what really direction these are in. So we've got a vector. We're going to use C there. Vector C, and it's made up of components A and B and A, because I just happen to write them that way. So we've got, here's B, here's A. So here's A is our Y component, and B is our X component. And we want to get the length of C. So the length, and this is where we use the double thing, C equals A squared plus B squared. So that's how you get the length. So does that make sense?
Right. Yeah, so the double quotes is the length notation as versus the vector notation?
Yes.
Okay. So yeah, and yeah.
I'm hoping I have that right. People notate it differently. I like if I'm. I don't think I normally use that. I normally just write length C if I'm like sketching.
Yeah,
this out myself.
That's more programmer-ish to me.
Exactly.
Yeah. Yeah. Okay. Yeah. I mean, that's not. Yeah. I mean, I can't pretend to be able to prove Pythagorean theorem, but I understand what you're doing right now.
Yeah. I wouldn't worry too much. I don't remember how to prove it either. But just knowing that that's the thing. So that's the situation to get a length, and hopefully that makes perfect sense. Okay.
It's good.
And then we get.
I need to get a label for my bottle. I have to have like generic.
I'm sure. Sorry. I'm sure it doesn't matter on YouTube. We're not taking sponsorship for this. It's fine. Okay. So and then, obviously, and then if you have like if this is our grid and this is like 1 and 1 and -1. And -1, and we got like we can do a unit circle around there, which tells us that would be the normalized form of C, which is written as C hat. That's basically C hat, which is the normalized vector is C divided by the length of C. So does that formula make sense?
Just hold on. This is where the what do you call it? The record skips. Like I understand I know what normalizing is intuitively. I know, the C hat is the little arrow right in the unit circle.
Yep.
Because it's only one. Because you normalize it to 1. That's C hat, and then the length of C. You're saying is to get C hat, what is C at the top? C is
C is just the vector C. So let me expand that out because I went through that really quickly. So first of all, if you take something that is the length of C, like say the length of C, and you divide it by the length of C, you get 1.
1.
And what we want is C hat. The length of C hat equals 1.
Right.
So what we're going to do is to get something that's the length of C to the length of 1, we're going to multiply it by 1 over the length of C.
Okay. You said that C was a vector, but it doesn't have its vector dashes on it. So it's a scalar or no?
Okay. So this is the length of C, which is a scalar.
Right. That makes sense to me.
So yeah, so that's what we've got over here. And we're multiplying this scalar by C, the vector. I'll notate my vectors.
Okay, yeah, cool.
And so the unit vector in the direction of C, so the normalized form of C, is equal to that. So we've got this one is a vector, and this one is a scalar.
Yes and yes. Okay.
So this might be like 0. Like that looks like 0.3 to me. So, and this might be like that's. Yeah, see, this is the problem doing it. Is like that's not the actual length of this 2 and 3 or whatever.
That's fine.
And then you multiply that by that, and you get an x and a y, which is going to hopefully be unit length, but it won't, because that's actually not the length or the inverse length.
Right. You want it to be unit length, which is 1 and 1, right?
Yeah, I mean, like I can bring out the calculator, and we can do this live.
Let's do it live.
Okay, so we're going to say I'm going to bring up a new sheet. Got plenty of space. Okay, so we're going to say that C is a vector that looks like this, with a y-axis of 3 and an x-axis of 2. So C equals 2,
X2,
3.
Yeah. Yep.
Okay. So the length of C equals square root of 2 squared plus 3 squared, which is equal to square root of 4 plus 9, which is equal to square root of 13. That's not how a calculator works, apparently. There we go. Which is equal to 3.6-ish. 3.6. So then if we want to get the normal form of C, which is like that.
Normal form, to me, we're just talking about enough information to deduce the direction, right?
Yes.
Removing magnitude from the problem.
Yep. So we've removed magnitude to get the normalized C. And so what we want is 1 over 3.6 times 2, 3, which is, there's an inverse button here, which is equal to 0.27 blah 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 27735. 5 times 2, 3 equals that times, whoops. So 0.5547 and 27735 times 3, 0.83205. Okay, so that's the value of C hat, which is the direction of C. Does that make sense?
I thought they would always be. What? Yeah, I mean, yes. So you did the math. So I get, like, I see that. For some reason, I always thought that these numbers were like whole numbers, but I don't know why I thought that. It wouldn't make sense otherwise. It would always just be 1 and 1. I'm probably confusing this with like matrices. And so I mean, if you put 0.55 and 0.83 on your graph, it would be the little red arrow.
Yeah, and that would be in the unit circle.
Right. Yeah. No, it does make sense.
Yep.
Yeah, I get what's happening now.
Good. So the thing to keep in mind with this, so what this is like usually used for is, say for instance you're making like the gorilla game with you got your banana and you want to send it out that way, and say the user clicks on like there and is like, I want to fire in that direction, but you want to fire it with a particular amount of power. So
right, based on how long they like held down the key or whatever.
Exactly.
Or, like,
so
yeah,
the user might have like power equals 3. So what you do is you then go like 3 times c hat is,
you scale it by the unit,
and that's like gonna be like the velocity vector.
Right.
And then you do physics on it.
But not today.
Yes. So that's sort of why you'd use a normalized vector. And the other thing to note is that obviously if you have a vector that's like 0, 0, which is like nothing, you're just sitting at the origin. The way this all works out is like you've got let's call it q hat equals 1 over the square root of 0 squared plus 0 squared times 0, 0. So that's the normalized formula. And what happens obviously is you get this term here turns into like 1 over 0 times 0, 0. That's obviously, you can't divide by 0.
Right.
So what you often do, depending on what your use case is, you either make sure that this is never 0, or you just detect, if this ends up being NaN or something out of the code, you just say, what I usually do is I just say, well, that's equal to a unit vector pointing that way.
Mm-hmm. Why don't you just try catch the divide by 0 and then I'm just joking. Bad programming.
Well, try catch is expensive, and a lot of times what you're doing in here is like in performance-y code. It still requires a branch, but you like check for not a number.
Yeah, I know. I was literally trying to make a funny, but you've explained it to if there's people watching. Yeah.
Yep.
I was not. I get it. Yep.
Okay.
So far, so good.
All right. How are we for time?
Probably way over based on what we want to get done, but I think we have to do dot product.
Well, I mean, I can save dot product and projection for later because it's probably not relevant to this at this stage. So let's skip forward and we'll save those for next time. We can always come back to them after talking about this. So what I wanted to do is I wanted to set some homework. So hopefully you've got like an hour or two to do this.
Yeah, I should.
And hopefully you've read through this document.
Yeah, I have.
So
Pong.
Basically,
making Pong.
Basically, I want you to make Pong, and I tried this like yesterday just to see what it requires and how long it would take, and it shouldn't take more than about 2 hours.
We're gonna be rich.
Oh yeah, this game sold so much. I don't see why it wouldn't sell a whole lot of copies if we made it today.
Bulletproof logic.
So, and basically the idea is we've got 2 paddles and we've got a ball and another paddle, and these things go up and down, and your ball like bounces around, and you're just in some space. The ball will hit that and bounce off. The ball will hit these and bounce off. If the ball goes behind that, this player gets a point. Simple as that. So, the only really difficult thing. So, I mean, yeah. So the whole point of this is really to see how you approach it and sort of get an idea of what's the hard things here, what's the easy things here, so we know what to look at later down the line.
So a whole lot of C hat going on here.
Well, possibly not. Like that may come in handy, but you don't actually have to use that. The things that you need here are collision detection. So sort of the point behind this is you actually don't need that much strictly vector maths going on. So we have one thing we do have is we have like, this is the position of the ball, and you have some velocity, which you basically, so you take the position of the ball, add the velocity, and you end up with the position on the next frame. So P1, P2. Does that make sense? Like, hopefully that really simple physics.
Just keep adding the vector based on whatever the velocity is every tick. Or maybe add some stepped, interval.
Yes.
To move the thing.
And so the thing is, you need to be able to detect when the ball hits the side of the thing and when it hits this side of the play area.
And it could be a fake boundary, right? Based on math rather than like having to worry about sampling the pixels or whatever.
So what I was going to say is, for a game as simple as Pong, and like a lot of simple games, it doesn't really matter if you, in fact, a lot of physics engines just do this. It's like, if it goes in there and you only detect the collision at that point, then it doesn't really matter.
Okay. Penetration has occurred where I'm going to snap it back, or just it doesn't, you said literally doesn't matter. We'll just reverse direction or do whatever calculation we care about at that point.
So, and then you're coming in at like this angle, and you come in at this angle, and that's like really drop dead simple vector stuff. And that is like, we've got the y of the velocity is going this way, and then all we do is we invert the y. So like the next step velocity is like x negative y.
And it's negative y and not negative x just because you hit the y-axis when you made the collision.
Yeah. So if you did negative x, you'd come back out that way.
Yeah. I'm just stupidly, clumsily asking whether you know which one to reverse and why you know that.
Yeah. So when you're coming in this one, the next step you'd have negative x and y.
Yeah.
And so,
right.
Like, I'm hoping that later down the line we can get into like actual physics and use some of this vector stuff, and then that's why we're going to need like the dot product and stuff. For if we have.
What did you?
Yes.
When we were doing the physics for like ricochets of weapons when they hit people, you referred to that in the engine code comments as inelastic. Is that what we're talking about here? Inelastic.
Yes. So okay. An inelastic collision is basically one where 100% of the energy going into the collision comes out. I think it's the energy going into the collision comes out of the collision. So an inelastic collision would be like exactly what we're doing here. You hit and then you come out with
right.
the same
Like
thing.
you're not deteriorating. There's no friction. There's no
Exactly.
like
Whereas in elastic
forces.
collision, pretty sure this is correct. Like this is one of these things where it's like the terminology. An elastic collision
Mhm.
might be like that, and you know, out, out of this, like in a physical sense, you get some heat and some sound and stuff coming
You
out.
might even you might even get the ball to change shape or convolute or whatever. Like the
Yeah, that's if you go like really sort of at the atomic level. I believe that the thing that's generating the heat is the fact that it deforms, and all of those atoms rub past each other.
Mhm.
I think that's
That's
how it
cool.
works.
That's a
Um,
little over my head, but I can kind of get it.
so that would be an elastic collision. I pretty sure. Um, but that's
I'm
sort
sure
of
you can post a little bubble whether you were right or wrong on the
well. This
screen.
is like exactly the thing. Is like I don't remember any of this stuff um, just off the top of my head, but I know that there's like such a thing as an inelastic and an elastic collision, and if it becomes important, I can just pop onto Wikipedia or whatever
Right,
and
right.
get
And
the
that's more the philosophy of how to make games is to know how to find the answer to the problem that you're trying to solve.
yeah. So what I was going to say about it is like just read a lot of stuff because I've got this like huge index, I guess, in my head of all of these things. I remember almost nothing about any of them, but I can always ask Google for the details.
Right. So you have like a secondary index, which is like basically things that you believe are true or things that you believe are possible. And
Yes,
then you have enough of that in your brain to be able to say, I know how to go find what I think is possible so I can remember how to do it, do the job, and then forget again.
yeah, and I mean it's not only going to Google like if you've got some problem, it's like, well, I need this to bounce like that. And I mean, this is obviously a really simple case. Like, I don't need to go to Google as such for that. I just sit there and work. Well, what does that look? What does that vector look like? Oh, this is inverting, so it's that. Like, I don't need to go and Google inelastic collision. And the same for
Right.
like this case. Like, this is obviously a much more complicated case because it's not axis aligned. Like, there's some actual like I can't just invert y
Yeah.
here, but I can do the vector maths, draw the diagram, and figure out what that means, like
I see.
how that works out mathematically. And I don't necessarily need to Google that. So for something like that, uh, that sort of mathematically simple, you just do that. I did want to mention like the what was it the you were asking about the sorting system for River City, um, and how like I came up with that.
Well, yeah, I think the question was, how did you like? I know you used what was it started with a T? Now I can't remember it. No, you used the 100.
Tarjan's algorithm. Hopefully, I'm pronouncing that correctly.
Yeah, yeah, right. So I mean, the question was like, how did you like? It's like sorting is hard. The 2.5D sorting is hard, and everybody approaches it differently. And I see different videos and different approaches. But you know, for the particular problem that we had in our particular engine
Yeah.
and spatial issues, you were like, I'm going to use Tarjan's algorithm, and that's what fascinates me is like how do you know that you like where did that come from? Did you have Tarjans in a bag in your index in your brain, or was it more that there's a class of problems you had an index to,
Okay.
and how did you decide that was going to work? I mean, and maybe I mean, you don't have to like break down the whole problem, but just how did we just how why does River City Ransom use Tarjan's algorithm and not somebody else's?
Right. So, well, there's like a three or so well documented algorithms that basically do the same thing, and Targins just happen to have some nice properties. Um, if anyone's watching this and wants to like look at that, like there's a underground video that goes into how it actually works. But the process of coming up with that, because that was really a complicated one. Part of it was like sitting down and drawing like literally hundreds of diagrams of like different prisms and stuff. If I have a box there and a box there, how does that work? And just really concentrating and thinking about all the different possible interactions to get a feel for that. At some point in there, it clicked to me that it's like, well, we're going to have to sort like 3 things, and there's going to be like a box here and a box here and a box here. At some point in just drawing a whole lot of stuff and really thinking hard about the problem, it's like, well, I don't need to think about 3 individual, like a group of say 3 boxes or a group of 4 boxes. What I can do is like, well, here's a pair and here's a pair and here's a pair. And that sort of insight led to the idea that it's like, well, that's a graph. And if we like want to sort that graph, it's like there's a whole bunch of drawings. I don't think I have my sketchbook at hand, unfortunately, but there's a whole lot of drawings on it. It's like, well, what is that like? If we start drawing out that thing, what does it look like? It looks like this. It's like, okay, well,
that's where like the things in the back fall down to the things in the front.
Yeah. So yeah, exactly. So you draw these ones first, and it's like, well, that's
this is depth slicing, isn't it?
Layer 0, pretty much. So that was sort of the initial concept, and I already I still haven't gone to like Google or anything at this point. I'm still basically thinking hard about this problem, and so I've got this. I'm like, at this point, once I figured that this is something we could do, it's like I'm onto something here, because I've divided the problem into like 2 things. It's like, here's how we sort. If we have pairs that we know the order of, like this, we can sort any number of them. We can sort an entire scene's worth. How we actually get this ordering was like another completely different problem. And there's
right, and I mean in earlier versions, and even in some cases now, we have that problem where the character's position will cause the graph to sort in a way that like the railing will disappear. Or
well,
what was that? Is that related?
Okay. So I'll get to that. But what I wanted to say was this particular problem. It was quite important to separate this out, like figuring out that this problem of sorting 2 things is distinct from the problem of sorting like n things.
Right.
So once you've made that distinction, this is entirely a graph problem. It doesn't matter what the shape of these things are. And I won't go into too much detail of how this one works. Like that's also in a underground video. Suffice to say, it does, and there was a whole lot of drawing and stuff to get this one. But over here, it's like, well, so the first thing you come up with is what happens if you get that pattern. So this graph kind of came first, and this one came second in the sort of the thinking process. And so there's like a diagram in my thing. It's like, well, what happens if we have a cycle in the graph? And I sort of started down the road of like, well, if we start grouping these cycles, like each cycle could be on its own layer. So it's 0, 1, 2, and then who knows what we're going to do with the cycle, but the rest of the graph stays sorted. And once I got it down to this point, once I had this diagram, that's the point where I went to like Wikipedia and Google And I'm like, well, this is now clearly like a graph theory problem. And like people have been working on graph theory for ages and ages. What do we have for like cycle breaking, and you know, what do we have that can do like that or something?
Okay.
So that this is like one of the harder problems that we solved for River City. And yeah, I'm not sure how much there is to say about it other than like it's a process of breaking down the problem until you.
Well, it's interesting to
Yeah.
me because it's like almost a lot of the time this is actually counter to what you hear a lot, like when you're, developer culture is like, don't reinvent the wheel, and which is you're not obviously, but the idea, the constant hammering home of don't reinvent the wheel, don't repeat yourself, blah blah blah. It actually causes you to think backwards. So like my intuition would be to, I'll go looking for solutions, whereas you've actually like take a slight risk and like reinventing something in the sense that you're like I've broken down the problem to graph theory and like figured out what those fundamentals are, and then now try to match that to existing practice, as opposed to rummaging around on the internet looking for other people's sorting problems, right? Downloading a
Exactly.
component for that, and then because the problem, now it's a lot better. It's a lot easier to keep control of that. I mean, a lot of people will go searching for a sorting solution and end up with, a NuGet package or some library they got to pull into their code, and then which I think you would call something like a cargo cult thing, where you have like a bunch of components that you don't know what's happening inside of them. And that happens a lot, and you pull that all in together to try to solve the problem, but now you have no control over the code and you still don't understand what's going on. You just assume that somebody else would have, but and it's not like that's not my approach either, but just the fact that like you forced yourself, like you said, hundreds of diagrams, so like there's a rigor there where you force yourself to really know what your problem is, and then you go looking in literature to find people who have made it more efficient, or who have taken it and even spent years of their life trying to figure out what the most optimum solution is. And that's why they have their names on the algorithms, right? Because
Exactly. Like,
okay, but that's interesting.
it's certain extent it's like a matter of practice and like taste. Like I knew once I got to like this point here that I could probably, if I sat down for a lot longer time, I could probably come up with some kind of algorithm that will break these cycles. But like I sort of have this idea in my head that's like, well, that's something that there's going to be someone who's actually made an algorithm and like proved out like it's big O, n squared or whatever. It's actually better than n squared. It's like O v plus e or something. I assume you know big O notation.
So 2 nested for loops is O(n) squared, and 1 for loop is O(n), and 1 statement is O(1), and like that's how I know it. I know it like from.
That's basically all you really need to know for game dev. So that's sort of the process. It's like, well, it looks like I have a really complicated problem here. Let's just quickly check if anyone who's like does hardcore computer science has actually worked out an algorithm and figured out like its complexity ahead of time.
Right.
But the other thing I will say is that knowing all of the like how this is built up and why it is all the way it needs to be, it lets you like do interesting things. Like if we just slapped this cycle breaking thing straight into the game without really considering it, one of the problems we would have had is like between each frame there's nothing to say that will break on one frame and then that won't break on the other frame, and like the sprites would flicker. And so knowing how to set this whole thing up so it's always the same link breaking, so you don't get like flicker frame to frame, That's
Right.
like,
That's like a determinism or stability in your calculation.
yeah, and that's something that you couldn't easily do if you didn't do all this prep work ahead of time to like
Right.
figure it all out.
Did we somewhat avoid the problem altogether because we decided to use fixed precision, did everything in integers, or is that not related?
It probably helped for this particular case.
Okay. I'm probably diverting from a, day
Oh,
one type of video, but
oh, I'm just like that's not like because we were all integers before this point for like physics reasons. Sort of, I hadn't actually thought about that, but I'm sure you could do some kind of stability thing with floating point. But yeah, doing integers makes it really trivial because it's like, yeah, well, we know we're not going to have like floating point comparison differences.
right.
So, what else have we got? We're almost at an hour, so
Yeah, I think we're good. I mean, we have some enough like the dot product stuff. We have enough to probably do for next time. In terms of the homework, I think there's going to be a lot of things that are not we didn't talk about obviously, but we don't need to talk about most of it, like XNA stuff or like
yeah,
getting input from the keyboard and that sort of
that's yeah. Well,
paint by number stuff.
that's all stuff you've done, and that's all like at some stage, you do just like need to read documentation for XNA or something. Because unfortunately, the documentation for XNA is terrible, but like
Yeah, I think I might use it as an opportunity to work with FNA, even though it's like a identical, but just like to set up my my workflow to be XNA proof, so I can kind of use like Visual Studio, beyond 2010.
yeah. Well, if you want any of the stuff I've done for that, I can send that to you because it's handy. I'll show you my stuff after. The only thing
Yeah, sure.
the only thing I wanted to talk about, which is going to be really quite handy, is I mentioned in the document because I did this exercise like to make sure it's doable, and that is you've got your paddle and you've got your ball coming in. How do you like collide them? How do you detect the case where it's like that? And I mentioned in the document.
Right. Yeah.
Minkowski.
I mean that only reminds me vaguely of like Euclidean distance and Minkowski distance and distance stuff that you use for like classification problems and machine learning, which is
Okay.
probably not related at all to this, but that's like the only thing I know about Minkowski that's sitting in my brain somewhere.
That will probably come in handy. What I was going to say is basically Minkowski sums is basically a way of adding shapes together. And I'll just draw out this case, and we can go into it a bit later. We use this a lot on River City for a bunch of collision stuff, and all of the separation stuff was built on Minkowski sort of ideas. There's videos about that too. So the idea is basically if we have a shape like that, and it's defined by a size, which is that represented by that vector there. So does that make sense so far?
What do you mean? Does it make sense?
So,
Maybe I drifted a bit. Yeah, say it again.
okay.
Sorry.
So basically we've got this is a paddle. It's represented by basically the half width and the half height. So if you wanted to draw, it at any position, you take say we want to draw at this position, we take the size vector and we say, well,
half of that,
we subtract it. We can put a point here. We can take, the, what is that? The x neg y is up here, and the same down in this corner is the y neg x, and we end up with
your paddle, yeah.
With paddle. So we've just basically picked a position and then used that vector that represents the half size to draw it at a position.
Okay, I'm with you.
And so the reason that this is useful is you can add the ball onto it. So if we have, there's the paddle, and if the ball is like this, we add that onto there, we end up with a shape that's like, here's the paddle, here's the ball. So basically ball plus paddle gets you this larger shape. And sort of the Minkowski idea is that, you know, if you add up every possible vector in this space, like the infinite number of vectors in here, and the infinite number of vectors that occur sort of inside this ball, you get the infinite number of vectors that occur inside this space. Does that make sense?
Yeah.
Cool. And the reason I bring this up is, say you've got like a ball coming in, like there. Well, if I draw this one first, that ball is about here. Whereas if I draw this one, that ball is about here, and that one is intersecting the paddle.
Right.
There, whereas this one is not intersecting the paddle. But what is important here is that this green dot is outside the added shape. This one is inside.
Right. Okay.
And so the sort of benefit of doing that is, rather than trying to do an intersection like that, like a rectangle versus a square,
like an AABB type of bounding box type of overlap check.
Yes.
Which is, I think, what most people would do.
You instead have this slightly bigger rectangle versus a point. And obviously that, just to program it, is way easier than like doing that one. There's a couple of ways to do this one as well that are sort of interesting. We can talk about them later. But
right.
Doing this ad hoc is actually harder than doing this one ad hoc. But I mean, you could do both.
You say harder in terms of computation, or do you mean harder in terms of...
I'd have to actually think, like, it's such a trivial thing that I wouldn't think about it from a performance standpoint.
Mm-hmm.
I think that this one, if you did it the naive way, this one requires more operations as well. But I just wanted to bring that one up just briefly, and this is like the really, really simple case of this, because it's what I found. Like, I'm like, while I was trying this exercise to make sure it's like, you know, nothing is in there that's like really quite difficult. I found that it's like, well, I can't be bothered sitting down and working out this thing. I'd much rather do this one, just because it's easier to check, is that point, is it greater than that one? Is it less than that one? Is it greater than that one? Is it less than that one? Whereas this is like, does that overlap? Like, this one is just, it's not as nice to calculate.
Right. Yeah, it seems make more intuitive sense on the other one. And I guess that you can determine the size of the box relative to the position. You only have to do that once, right? Or do you have to move it around every time? I guess you would. To determine whether your position's in the rectangle.
So what you would do, what you would do is you'd do the addition just in a non-spatial way. So you start with this vector, and then you add that vector, and it's like, all right, there's my added vector, which tells me how big that outer rectangle is. So I've got that.
Right. And
then you'd place it, and then figure out the bounding box, and then figure out whether the bounding box, and then figure out if your point is in or out of the bounding box. So that is not critical to doing the Pong game, but it makes life a lot easier.
Yeah, and it's something new to learn too. Because, like you said, you ended up using it for other things, and it's one of those things I'm going to want an index for. In my brain.
Exactly, it's actually a really useful technique, and obviously, and we'll probably go into this later, but if the ball was a circle, you'd end up with a shape. You got your paddle, and then you add on the ball, it ends up looking like a rounded rectangle. And obviously, I can't draw, but if the ball happened to be round, you'd end up with a shape like that.
Right.
And then here the ball is outside, here the ball is inside the paddle. And there's
I see. So you actually have a way to get around artistic problems. Is that what you're saying?
Not as such. So there's another way of detecting this case, which I want to get into because it's quite interesting. That isn't quite the same thing as a Minkowski sum, but this case is useful, particularly if you can work out if you're inside or outside a rounded rectangle easily. If this inside-outside problem is easy, then that's a good way of doing it. If this inside-outside problem is hard, if the ball is shaped like that, we end up with a shape like that, or something. Obviously, that's not a useful thing to reason about. Whereas this shape, that's really easy to reason about. So that's a good use for that technique. On River City Ransom, we happened to be in a position where we could optimize a whole lot of things, because one of the shapes was a rectangle, and the other shape was it had some interesting properties, but it was basically that. It was always smaller on the top, but what you could do is build that rectangle up around and basically move that rectangle around all of the points, and end up with a thing that looked like that. And we actually did a filling system where we actually made a bitmap on the fly that was that space there, which we could then collide against. It's that point's outside, that point's inside.
This is the masking.
Not as such. I can go into more detail, but there is a underground video on this.
No, I haven't done my homework, obviously. I was too busy programming moves and stuff. I'll have to watch them all.
Yeah, absolutely.
I'm outing myself for having not watched them all.
That's fine. We've been very busy, but the point is literally that was a bitmap that we generated on the fly. It's. Man, I'm such an artist. We would fill in all of the pixels that shape touched when it was combined with a player. so that then we could just scan like, and then it's like, oh, here's a place where the player can stand. So that was how we used it. So we used it sort of in this fill in the space with the infinite number of vectors, or because we're pixel based, we don't have an infinite number of vectors. We have like they can only land on pixels. So we could actually use that technique in that way. Whereas what I'm suggesting for this particular case is you just work out the boundary and say, which side of the boundary are you on?
Okay.
Hopefully that made sense.
Yeah, I mean, I think I'm reaching my saturation point, but I think I get it like visually.
I wouldn't worry.
I get it concretely is different.
I wouldn't worry too much about the River City Ransom stuff. Just the fact that you can make a bigger rectangle and detect against a point is all that's really useful for now.
Okay.
And I sort of wanted to include that also because it's like, here's a vector addition that we're doing. Just to make sure that there's some sort of practical element for the stuff we worked on, and then like there's the picture of the thing, but you've seen that. All right, let's call it, and we'll come back next week, and send me your thing, because I will go over it and see if there's anything we need to focus on particularly, or if it's like ends up being trivial.
Great. I can do that. I contemplated doing it live, so to speak, but I'm not sure if I will. But if I can find that amount of uninterrupted time,
makes sense.
Then it might be useful to just do it from the blinking cursor and record the whole thing, because then it's clear and obvious what my process was. And I'm not sure if that's useful or not, but I'll try it. But worst case scenario is I'll just write the code.
Yep, that makes a lot of sense. And hopefully it's pretty straightforward.
I think I've made Pong a few times, but maybe not with Minkowski. So it'll be good. It'll be fun to get going on it. If I use your boilerplate, it'll take away some time of like setting up, like looking for the packages, and OMG mono game isn't running for me when I file a new project and all that other stuff. So.
Yeah. All right.
Cool.
Let's call it. Thanks, Daniel.
All right. Thank you. See you next week.
See ya. Go find OBS.